before going back to the slides, I just made a little sketch for you which says we have this structure function in the proton, and it depends on two variables, x and q squared. Of course, there are different ones for quarks and gluons, but different machines have different kinematic ranges of x and q squared that they can probe. The original fixed target experiments had a 20 to 50 GeV electron beam and on a stationary target. So they were only able to get to q squareds that were a little above 100 maybe. And so that was this range. And they could not go to very large x. If you think about the kinematics, that forces you to go to smaller q squared, and pretty soon you're below q squared equals 1. But then Hera came along, and it had like a similar energy electron beam, 30 GeV or something, but it had like an 800 GeV proton beam. And so it had much larger center mass energies. It could go to both higher q squared and also much smaller x. And there were surprises about how many gluons there were at small x. And then the Hadron colliders came along, and the Tevatron could reach much higher q squareds, but of course not nearly as high as the LHC. They're not doing deep inelastic scattering, but they are probing the structure functions in a way that depends on which process they look at. And in general, the invariant mass of the final state is roughly the S hat of the collision, which, as we saw before, was the total center mass energy times x1, x2. And if these are approximately equal to each other, then the typical x is just the square root of S hat divided by the square root of S, or the mass of the final state divided by the square root of S. So for example, the LHC has 14,000 GeV center mass, and T plus T bar is 400 GeV. So that's somewhere around, maybe it was supposed to be 10 to the minus 2. Probably was supposed to be at 10 to the minus 2. Anyway, when you go to something smaller, where the mass is about 3 or 4 times smaller than the mass here, then you get somewhat smaller values of x. But the LHC can also probe much lighter systems that have, such as BB bar production or J psi production. And in that way, they can look at things at very small x as well. Of course, the new physics region, typically you're thinking of heavier particles, and that would be at more moderate x. So this is just another, going back to this slide about the general factorization formula. I'm not going to really derive it in any sense. It's basically the same picture as in deep inelastic scattering, heuristically, except that the other side of the process is also supplying partons as well. Now, there are a lot of subtleties in applying it in hadron collisions. Some of those were shown schematically in that first slide I showed. And they involve the fact that there are proton remnants on both sides. That is, parts of the proton that don't correspond to the partons that collided that can also interact with each other. So that's called multiple interactions. And those are modeled by Monte Carlos. People are trying to put them on more rigorous ground. But it involves more complicated distributions, double distributions, which depend on more variables. And the data is not nearly as good as for the leading twist contributions. There's also just the underlying event. Even if two partons don't collide, the proton is disrupted. It scatters a whole lot of soft stuff all over the detector. That also happens to some degree in EP as well, depending on how closely you want to look at the final state. So now the next issue we need to talk about in QCD is that we can't predict everything in the final state. And the reason is that the coupling constant becomes very large at long distances, and we need to make sure that our observables sort of focus all the interesting part of the problem to short distances. To be more concrete, when we start looking at specific contributions at next to leading order, which we'll do in a little more detail later, we find that if we have some leading order process, there will typically be two types of radiative corrections. One where we emit either a gluon, say collinear or soft, or a collinear quark, or we also have virtual one-loop corrections. As Eric was pointing out in his lecture earlier today, these contributions can have soft divergences, which he pointed out in the case of two massive lines exchanging a massless vector. But if these lines are massless, there will also be virtual collinear divergences, where the virtual momentum is parallel to one of the external legs. So the soft singularities in momentum space, when you regulate in dimensional regularization, will generically have a form that is logarithmic in the magnitude of the soft momentum, but instead of getting a log divergence, you'll get a pole in epsilon in the difference of the dimension from 4. And however, this behavior will tend to factorize in terms of some lower order cross-section that you reduce back to when you remove this momentum. And there's a similar divergence in collinear limits when these two guys are parallel to each other. And on the virtual side, when you do the virtual integrals, you have very similar expressions appearing. And in fact, there's a general theorem, Kinoshita, Lee, and Naunberg, that all of these virtual and real corrections should cancel. But in the case of QCD with these mass singularities, you should make sure that your observables are insensitive to both soft and collinear radiation. So if you have something that's collinear sensitive, then it will happen very far from the initial collision, because the virtuality of the particle that splits into two collinear particles can be very low. When that happens, you move out of the regime where you can do perturbative calculations. So there's sort of a general criterion called infrared safety that you should apply if you want to do a standard perturbative calculation of a quantity. So these observables will always involve or have to be defined on configurations with a generic number of partons. It's just like in QED, you know that you cannot ask for 0 photon radiation when you have charged particles in a process. Any electron coming out of a collision at high energies is going to be accompanied by some soft cloud. And you could do something like measure the energy of the electron, but you can't require that energy to be exactly its initial value, or you'll get 0 for the result. And similarly, we need to define in QCD things that are valid, or the observables should be defined for generic parton configurations. And there's a smoothness constraint, which is the one that basically tells us that they're short distance dominated. And that is that if we take any particle to become soft, because that particle might have been a gluon, and we have strong soft gluon emission, the observable should behave smoothly as we remove that momentum. And also, if we take two momenta to be parallel, like Ka and Kb, in that case, the observable should also be smooth. Some examples of things that aren't smooth, and therefore they can't be predicted perturbatively, would be something like the number of partons in an event. Well, you can't even measure partons, but if we imagine that partons somehow match to hadrons, and we want to predict the number of hadrons. That's also something we can't do in purely perturbative fashion. So the number of partons, that changes discretely in collinear limits as a quark splits to a quark or a gluon, so on. So that's an example of something you can't do. An observable that forbids radiation in some region. So sometimes experimentalists will define classes of events that require there to be no hadrons in some patch of the detector. But that's the sort of thing that when you forbid soft radiation from going anywhere, it's like forbidding soft photons in this electron cloud. You won't be able to predict how often that happens. Another thing that you can't predict is the production of a particle like a W or a Z or a Higgs. These are all colorless particles, and they're produced by the collision of two partons. For example, QQ bar makes a Z. But this Z has a generic momentum parallel to the beam, but also could be perpendicular to the beam. But the distribution becomes very singular if you ask for distributions very close to with PT near zero. The transverse momentum of the Z is, if we just emit one gluon, proportional to the transverse momentum of the gluon, and that's a collinear singularity of the type we saw before that looks something like dpt over pt. So it's a very singular distribution. There are ways to resum the distribution to give you better control near small pt, but precisely there is something you can't do easily. And if we go back to the electron-proton scattering, again, just to get another look at what infrared safety means, the quantity we were considering there, which was basically just involved the lepton kinematics. These structure functions summed over all hadronic final states with a given invariant mass, didn't ask any questions at all about how that hadronic energy was distributed. And that is something that is perfectly okay. It's totally inclusive. If one outgoing parton splits into two, the total invariant mass stays exactly the same. Or if one soft gluon is emitted, doesn't change the invariant mass. So that's perfectly fine. Of course, if we go to something like a totally different configuration, like the x goes to one limit, which corresponds to elastic scattering, in this case, this is totally different. And the physics of the elastic scattering is that it will never happen unless the large momentum transfer. It never happens unless these quarks are very close to each other transversely so that they can actually communicate when one of them is struck by the virtual photon. So this is a case that can be described, but not in terms of parton distributions. You need to use light cone wave functions for the three valence quarks to try to describe this. Now, this is a very rare event compared to the total deep inelastic scattering when you take Q to be very large. But it's an example of something you can't describe in the parton model. Another thing you can't describe, which is purely perturbatively, is something that it was a big contribution. About 10% of the events at Hera had a distinct gap in particles. And the interpretation was that the proton you didn't directly extract a quark from it. Instead, you extracted a gluon because there were a lot of gluons at small x, which then interacted with the virtual photon through this process with QQ bar produced. And then another gluon came along to neutralize the color that was being exchanged here. But when you have a color singlet here, you have the possibility that there's no particle production in between, that we don't have any color strings that will rip hadrons out of the vacuum and distribute them everywhere. In other words, you saw localized depositions of hadrons, but then a gap to the forward proton. Anyway, this is a common event in electron-proton scattering that has a different structure and can't really be described in the same way. Now, going back to the LHC, now we'll go to the good news. Many things can be computed perturbatively because they are infrared safe. And if you produce a color singlet object, then almost every kinematic variable for that object can be predicted because the other partons that were involved in its production are not generally, you're not generally sensitive to their kinematics. This PT equals 0 is one exception. But in general, most of these kinematic distributions are perfectly calculable. Photons are a little tricky. Unlike, these are all massive electroweak objects, but the photon is massless, and it can be produced in a non-perturbative way by a quark fragmenting at very low scales to a photon. But when this fragmentation happens, the photon is usually accompanied by a lot of hadrons. So there are isolation cuts that you can define to try to suppress the non-perturbative contributions to photons. And then the case I'll say a little bit more is the hadronic object that dominates the LHC physics, which are jets. So in order to define jets, you have to find a suitable algorithm that makes manifest this infrared safety. Actually, at the Tevatron, the default jet algorithms turned out not to be infrared safe. But this was only discovered after they were pretty locked into the analyses. And so they were safe for 2 jets, but not for 3 jets. So at least at the orders that had been calculated at the time. But at the LHC, the good news was that theorists understood infrared safety well enough before the detectors had latched onto their jet algorithms so that they were able to adopt one default one that is safe. There are different kinds of algorithms, but the one used at the LHC is a cluster algorithm. And the idea is that you start with a list of objects, which ideally would be particles. In practice, they would be calorimeter clusters and maybe tracks in some cases. And then you also add the beam to the list. And then you define a distance between these particles and arrange that it vanishes suitably. Well, in fact, it doesn't exactly have to vanish, but the one that's used is the minimum of kT, the transverse momenta of the particles, times the distance in this unrolled cylinder. So the distance depends on the azimuthal angle, which has a nice rotational transformation, and then the pseudo-rapidity, which we mentioned before. This log tan theta over 2 behaves well under boost, so it's usually used as the sort of transverse separation, and then it's weighted by these kTs. And the kT that you take the minimum of can be raised to different powers, and different powers have different properties. So the original one that was used in E plus E minus was called the kT algorithm, and that corresponds to that power n up there being +2. And so it tended to cluster, I think, collinear stuff first and soft stuff later. But then, no, sorry, I think I have it backwards. But that gave very irregular looking jets that were not very useful for hadron colliders. And then Gavin Salam realized that if you switch and I guess Cacciari, switch the exponent from 2 to -2, then you change the properties and you made the jets much more circular, which made it a lot easier to estimate various sorts of contributions that go beyond perturbation theory. In any event, these cluster algorithms, because they operate on this hierarchical principle, they tend to be completely unaffected once you go into these soft and collinear limits. And so they give very nice, safe definitions of jets that are used. And the default one that's used right now is anti-KT, is used in almost all basic jet studies. When you do some other more sophisticated things, like jet substructure, then you can sometimes make use of other algorithms. So this is basically a very powerful tool. Now, one thing I needed to stress is that this factorization that we wrote down for the hadronic cross-section is depends, the different pieces depend on the factorization scale. And so if you like, we can draw a box in physical space, although the factorization scale is really in the transform space, in momentum space. But as we vary the size of the box, we can see that different processes will appear. So as we move from a few GeV up to MZ, we see that the interpretation of what's going on with this given process changes. In this case, the gluon that's emitted there is being thought of as part of the short distance cross-section. But in the second case, at the higher factorization scale, that gluon, or rather the quark that it has a different momentum because it's radiated that gluon, it looks like the structure of the proton has changed. So there's an interplay between the short distance cross-section and the parton distributions. Both of them evolve logarithmically due to processes like this as we change the resolving power that defines the short distance cross-section. But they should compensate, and the results should be independent of the factorization scale. Now in practice, whenever you do a truncated perturbation theory calculation, the cancellation is not quite complete. And you can use that as a measure of the uncertainty. But this change of the structure is captured by an equation which is called the Dglap equation, originally the Alterelli-Parisi equation. And it states that the logarithmic evolution of partons is due to collinear splitting. So the effect at large scales mu can be described perturbatively, where a distribution function like a quark will have an evolution which is governed by other partons, could be the quarks, could also be gluons, that evolve into that parton through B evolving to A. So you have to kind of read it from right to left. And this P is a collinear splitting probability. Now, before the end of this lecture, we'll see how you can relate these collinear splitting probabilities are basically the squares of splitting amplitudes that you can read off from the spinor helicity forms for the amplitudes. But for now, just take my word for it, that these have been calculated originally around the same time as the discovery of asymptotic freedom, in some cases by the same authors. And then they were calculated to successive higher orders in perturbation theory at next to leading order in 1980, around 2004 to go to N and LO, And some of the same authors who worked on NLO have been involved with the n-cubed LO, for which there are partial results already available, but not complete yet. So this is the fundamental equation that is used to fit data that is interpreted in terms of parton distributions and move that data from one value of q squared to another value. Q squared and mu here are more or less the same, and mu squared are more or less the same. And this is an integral differential equation, but it can be diagonalized by going to Mellin space. And in Mellin space, it's interpreted as anomalous dimensions of these operators. So there's a relation that is so let's take that, let's see, how much time do I have left?
15 minutes.
Okay. Let's take that equation up there and so this operation of integrating a function of xi and one of x over xi in this way comes up all the time. So it's often just written as a shorthand with this tensor standing for the convolution. Let's take this equation here and let's act on it by integrating from 0 to 1 dx x to the n minus 1 of this. And let's see what happens, what we get on the right-hand side when we do that. Neglecting overall factors, we get integral, we have an integral from 0 to 1 dx and an integral from x to 1 of dxc. So we're going to change variables and rewrite it by doing the integral, move the integral over x inside. Then the integral over xc goes from 0 to 1, and the integral over x goes from 0 up to xi. And then we can pull fb out front because it doesn't depend on x, it only depends on xi. And then over here we have x to the n minus 1 because we put that in when we put in the integral over x. And then we have PAB of x over xi. So now we can put a xi in the denominator here, and that was n powers of xi. So we need to put a xi to the n here. But now you see that on the left-hand side, we had mu squared dd mu squared of the integral 0 to 1 dx x to the n minus 1 of fa. And on the right-hand side, we have some factors. And then we have the exact same thing again, except it's in terms of C. But that's just a dummy variable. And then over here, we have, if we just call this x over c equal to z, we have the integral 0 to 1 dz of z to the n minus 1 times PAB of z. So these quantities here are called the Mellon moments of the splitting kernels. But not surprisingly, they are the anomalous dimensions of these matrix elements, because this quantity here is exactly what's appearing here. It's just evolving with a gamma AB. Now, this is a matrix in general, because quarks can split to gluons, gluons can split to quarks, and so on. But you can partially diagonalize it by rewriting your basis for quarks. So if you have qi minus qi bar, you consider not just the quarks, but the difference of quarks and antiquarks. That is odd under charge conjugation. And that won't mix. You also have qi plus qi bar, which is even, but you can subtract off another flavor. And then you can make it non-singlet under flavors. So this is called the non-singlet distribution. And then there's the singlet distribution, sigma, which is the sum over I of qi plus qi bar. And that's the only one that you can't completely separate from the gluon distribution. So this matrix gamma AB is block diagonal. These guys evolve separately and can be treated as just one-dimensional evolution, where the matrix becomes numbers. But the sigma becomes two-dimensional, or stays two-dimensional. So there's a mu squared d by v mu squared of sigma g has the form, well, let's say we go to the Mellon transforms, which I'll just call sigma tilde and g tilde. Then there will be these gamma qq of n and 2nf gamma qg, gamma gq, and gamma gg. So this part stays as a 2x2 matrix, but you can diagonalize it and compute its eigenvalues if you need to solve this evolution equation. So once you do all that, do some beautiful fits to a large amount of data, you get this sort of description of the structure of the proton. And here are two different fits from last year or the year before that show x times f. And they notice that there's a what we call the valence bump up here, UV. That UV means U minus U bar, and DV. And look, there's about twice as many U quarks as D quarks, valence, in the proton. And they show up at about 1/10, although the exact position of the bump depends on the scale. As you evolve to higher scales, the things with larger momentum, they evolve downward because of the nature of this kernel. They can only sort of evolve downward. And so the stuff at lower x gets boosted up, and the valence stuff is sacrificed. And at small x, there's an enormous rise in the gluon. You see the gluon's already been divided by a factor of 10 to try to keep it on this plot. But you remember when we make Higgs bosons, the kinematics is such that it's somewhere around 10 to the minus 3 or so. And so this enormous gluon luminosity is one of the reasons why the gluon fusion channel, glue to Higgs through a top quark loop, is the biggest cross-section for Higgs production. And of course, there's also huge production of B's and C's, which were generated from the gluons by further evolution as gluons split into heavy quarks. And nowadays, since Hera has not been operating for a long time, and the LHC continues to take more and more data, the PDFs, while being used to make predictions for backgrounds that allow for the search for new physics, at the same time, they are also being fit to LHC data because the data is coming in. One example of data you can fit to is the production of W's and Z's. This shows the total cross-section for W and Z's in the region that the detectors can see, the fiducial cross-sections. This is ratios are good because a lot of things drop out. And this is the ratio of W plus to Z. This is the ratio of W plus to W minus. And the experimental result is actually the wide yellow band. And the predictions depend on different groups who do the PDF fitting in different ways. They get slightly different distributions. In the case of W plus to Z, the data here is not yet, for just this total cross-section, cannot yet distinguish these, although here it disfavors one of these fits, ABMP 16. They can also measure not just these fiducial total cross-sections, but how they're distributed in rapidity. And when you do that, you get more information because the one-dimensional rapidity distribution lets you sample different x1s versus x2s. As x1 is bigger than x2, you push the W or Z forward or the other direction. So these curves have additional information. In fact, they don't seem to fit very well to most of these distributions. And I'm wondering if NNPDF 3.1 was actually partly improved by taking into account some of this data. So you can see that there's kind of none of the data sets here fit too well. Over here, the fit is better for the W plus W minus asymmetry. Anyway, this is still an ongoing process. I think, let's see, maybe I'll just show 2 more slides quickly. One is just the statement that the job of a perturbative QCD person, if you're not involved in fitting the PDFs, is to improve the accuracy on various short distance cross-sections. And the expansions, typical expansion looks something like this. There's a leading dependence on alpha S that depends on the process. Drell-Yan or Z production would have 0 here. Jet production would have 2. Dijet production and other more complicated processes, higher powers. And the real problem is that a lot of these leading order predictions have very large uncertainties that are you only start to be decently accurate, that is around maybe 20% at next to leading order. And if you want to go to below 10%, you usually need to go to N and LO. And the good news is that a lot of processes, an increasing number of processes are available at NNLO, as well as a huge number of processes at NLO. And finally, what is the sort of role of amplitudes in this game? They enter the cross-sections in the following way. At leading order, the only graphs you will ever need are tree graphs, as illustrated here for Z production. At next to leading order, the contributions to the cross-section include virtual corrections, but because you need to define processes in an inclusive way and allow for additional radiation, at the same order in alpha S, that is 2 powers past Born, that you get one loop interfering with tree, you also get the square of tree graphs with one additional parton. And in general, there's always a possibility of radiating an extra gluon into the final state. But in most cases, you can also change a quark in the initial state for a gluon that splits into QQ bar. And you get extra channels opening up, extra dependence on different parton distribution sets, combinations. And these only cancel after you have done phase space integrals here that lead to positive divergences, which you usually regulate with dim reg. They cancel negative divergences over here. And similarly, when you go to NNLO, here we basically have virtual plus real. At NNLO, you can have doubly virtual, 2-loop amplitudes. You can also have mixed virtual real, where you have 1 loop and 1 extra leg. Or you can have double real, where you have tree-level amplitudes with 2 additional partons. In this case, the IR cancellations are even worse. If you regulate things dimensionally, you have to go cancel things from 1 over epsilon to the 4th to 1 over epsilon. So in the last couple of lectures, we'll get into a little more detail of the structure of the collinear divergences. To some extent, look at some of these phase space integrals and see what some of the corrections look like for simple processes. So that's all for today. Any questions? Yep, Jan?
I would say that the most important impact of HERA was then to produce the PDF data.
Yeah. It's, the thing is, you can't do everything with HERA alone. For example, you're sensitive to up quarks with 4 times the sensitivity to down quarks because the charge ratio. But you always have this sort of same combination coming in. And so you need other data sets in order to try to separate out some of that. So Drell-Yan and fixed target was used for a while too. And you also don't see the gluon directly at HERA. At small x, you actually see the gluon quite well, effectively, because the violation of scaling, the q-squared dependence, the log q-squared is very strong. And that's because the large gluon at small x evolves into quarks, changes the quark distribution, and changes F2 quite strongly. But at large x, the gluon is small, and then you just can't see it at all. So then people use jet production at hadron colliders. That has a lot of gluonic contributions to it, but it's not as precise theory, and it's harder to measure jets. So there's a lot of debate between different groups about which data sets to use, which influences some things. Like if you only use HERA data, you can see the gluon distribution, but it's tied to alpha S because you see it through the splitting, which goes like alpha S. So there's also a degeneracy with alpha S. Other groups try to take alpha S from an external source, and then that changes the fits. But HERA played a huge role. It also led to a big surprise. It wasn't realized how big the gluon would be at small x, and probably even at the x's that you need for Higgs production at the LHC. Any other questions? Yep.
At what point can you stop testing the validity of this kind of approach?
Well, I mean, you can take an inclusive process and then you can go and take q squared below 1. And then it's, pretty.
But at like really small x, you have.
Yeah, so when you have these large densities, you may worry that even when q squared is large, the density of the partons is so high that there are saturations. So there were old studies of this, like Gribov, Lipatov, and Rishkin discussed how some of these sort of more nonlinear effects would occur. I don't know that they've been visible at the LHC yet. I haven't kept track of that. Maybe some people have done it. There's also, just when you go to small x, you find that the splitting kernels have a singular behavior in that direction. And so not worrying about nonlinearity, but just trying to improve the approximation for the linear evolution is there's a small x resummation you can do. And I think it's probably useful, but I don't know how dramatic an effect it is because I haven't looked at that in detail. Large X is also another tricky corner. The real q² expansion should be more like 1 minus x times, or q² over 1 minus x or something. In other words, things get non-perturbative faster than you thought they did when you push up towards x equals 1, I think, a bit. Any other questions? If not, I guess this session's adjourned.